I have the pleasure to introduce Dr. Harrison Martin. Harrison is a fluvial geomorphologist and sedimentologist interested in how water and sediment move, shape the landscape, and become recorded in the rock record. He did a master in geoscience at the University of Calgary and then the PhD at Indiana University in the USA. Now he is a postdoc in the Division of Geological and Planetary Science in Caltech, still in the US. And today, Harrison will present us his work on global source-to-sink and geomorphic process domains to show us that land is mostly diffusive and eroding. Thanks a lot, Harrison, for being here, and stage is yours.
Awesome. Thank you very much for the great introduction. Are you able to hear me all right?
Yeah.
Awesome. First of all, thank you so much for the opportunity to be here. I appreciate the invitation and all the work behind the scenes putting on this series and organizing. It's a real privilege. There's been a lot of great talks through the series, and I'm happy to be here. And yeah, so my name is Harrison Martin. I'm a postdoc here at Caltech, as was mentioned, and today I'm going to be sharing basically the first two projects that I are coming out of my work here. So without any further ado, I do want to take just a minute or two before I get started to talk about myself, my own work, and my own journey to get here. I was born and raised in Hamilton, Ontario, where I did my undergrad at McMaster University with Jaunik Bhattacharya. And there I was working on fluvial sed strats. So this was me looking at the deposits of Cretaceous era rivers, trying to figure out flow directions, tramping around Hanksville, Utah for a summer. Moved west to Calgary, where I spent a number of years working on a master's in, again, fluvial sed strats. So I logged about 4,400 wireline well logs and 2.5 kilometers of oil sands core, trying to put together these maps of different intersecting sand bodies in the subsurface. What time did they come in? How did they intersect? And what's the 3D geometry? And what can we learn about the depositional environment? And that was a lot of fun, but eventually I decided I want to learn more about modern rivers. I wanted to figure out geomorphology and mathematical modeling and a lot of computer science. And so I went to work with Doug Edmonds for a PhD at Indiana University. And then that eventually led me here to Caltech, where I'm in the third and final year of my postdoc. And as someone who is in the third and final year of his postdoc, I'm of course on the tenure track and postdoc job market, so I've been practicing describing my own research program. So if I can get a little more practice, I like to say that I'm a geomorphologist, a sedimentary geologist, and I like to look at lowland depositional environments, particularly. So the way I kind of frame my work is I start from the smallest scale, the landform, and in my PhD, I spent a lot of time looking at river bends and how the banks migrate and evolve over time. What are the physics that describe how rivers move? And for here, I used drone-based LiDAR in order to get frequent observations. I collected 22 drone-based LiDAR scans of a single river bend for 4.5 years. And we take the physics that we learned from the bend scale and use that to inform the landscape scale. So then another project that I've spent a lot of time working on is how do these mountain front landscapes evolve, and how do the river physics and dynamics contribute to shape landscapes and build the rock record? And because this happens over a much longer time scale than we can observe easily, this is something that we handle usually using numerical modeling. And finally, we take the landform, the landscape, the basin scale, and think about the Earth as a whole system. And this is where it comes in with the geospatial analyses, scientific computing, data science, and all that fun stuff that's really marked my postdoc. Now, that's the kind of work I do, and that's the methods I use, but how do I design research projects? This is something I learned from Doug, and I just love the idea of testing and identifying community hypotheses. So if we can identify what assumptions we collectively make as a field, we can then test them, of course, but we can also look at some of the unspoken implications of these assumptions. So how does this affect the way we look at the world and the consequences, and you can explore them. And so the two I'm going to be presenting today kind of test these community hypotheses. The first is on source to sink frameworks. This is work that was published in Geology last summer with Mike and I. And the second is on landscape evolution modeling, which is near and dear to a lot of people in this room, this community, and that's a paper that's currently in review. So starting off with the source to sink framework, it is a dominant community hypothesis. It's a great example in that it is a way that a lot of us look at the world through a lot of disciplines. And it's very useful. And if you ever crack open an introductory geology textbook, you'll probably see something that looks like this in 1D, or here's a 2D representation. And it's a way that we kind of split the world up into areas that are eroding, the sediment sources, that's that blue-purple area, often the uplands of the world. And then the sediment, is eroded from there, and we see it make its way through the lowlands of the world, through bypass zones where it's temporarily stored, but doesn't really have long-term preservation potential, and into the sinks of the world. These are the places that actually are subsiding or otherwise degrading and building the rock record. So we split the world up into these kind of three categories. And when I learned this, it seemed like it was an idea as old as time. But in reality, it wasn't formalized until '82, when some works on the east coast of the USA really put names on it. And however, since then, it's been used prolifically across a lot of disciplines. So the oil and gas industry or resource exploration in general gets a lot of use out of it. The idea of global carbon cycles. It's useful in understanding how organic carbon moves through rivers. That's a different field I'm working towards. But also in terms of the global carbon cycle through geologic history, the silicate weathering that kind of cools down the earth over the tens of millions of year timescale. That happens in the source regions. And of course, in understanding how sedimentary environments and signals get preserved in the rock record, and understanding that that only happens in those green areas, right? Those are the only spots that can actually bury sediment beneath reworking depth and build the rock record. So it's an important thing to understand. But I want to step back and just ask at a basic level, does the world actually look like a source to sink diagram? Certainly there are places that do, right? You can find a number of catchments around the world that look like that 2D plot. It's clearly been useful and has worked well enough for a lot of stratigraphy, but as a whole, does the Earth look like a diagram? And if not, what would it look like alternatively? And what would be the difference between places that do and don't? And so if we want to answer this question, we need to map the world as if it was a source to sink diagram. We need to classify every place, every pixel in the world as being a source, a sediment source, bypass zone, or sink. So we need some kind of classifier, right? We put information in, and out the bottom it spits out which of the classes it is. This doesn't exist, so let's build it together. And the method we're going to use here is a decision tree. Just like if you took an intro geology class at some point and you did a mineral identification, is it lustrous? Okay, well, you go this way. Can you scratch it with a penny? Okay, well, it goes this way. We're going to use a decision tree, except this time each of the decisions is based on a data layer, some kind of input. So for the first one here, is it within a global islands data set? Is it on land, essentially? And right away, we can say 3/4 of the area that I studied, which is everything but Antarctica, essentially, is ocean, which is a sediment sink, but it's its own type. And we go through a series more decisions. I'm not going to walk through each of them with you, but it's an iterative process we design in order to create this kind of classifier. I am going to take time to highlight two data sets, though, specifically, that did a lot of the heavy lifting in this work. One of these is by Bjorn Nyberg and John Howell back in 2015 in geology, where they did a paper I really like. It's a test, again, of a community hypothesis, this idea of that the present is the key to the past, uniformitarianism. Facies modeling, if we want to understand how to interpret the rock record, we should look at the modern equivalent environments, look at the bed forms, think about how they relate to stratigraphic, sedimentary structures, I should say. But the motivation behind this study was not the whole world is going to be preserved in the rock record. Only bits and pieces, only the stuff that's in sedimentary basins. And they mapped out 16% of the modern Earth land surface is a sedimentary basin. So it's a cool work, and we use their results, but I want to highlight a little thing where they talk about active or modern sedimentary basins. And to illustrate this, this is the Amazon River Basin. And if you're familiar with the Amazon River Basin, you'll know that there's a lot of sediment. it is a basin that is full of sediment, and yet that yellow strip on the left only really goes along part of the river. You know, there's a lot of lowlands in between. How come that's not a sedimentary basin? It is in a stratigraphic term, but the reason it's not classified is because it is full of sediment. It has reached capacity for a few million years now. For every river that sheds sediment off the mountain front, if it gets past the foreland basin, the idea is for every extra kilogram you put in the front of the river, the same number of kilograms is going to come out the other side, averaged over some long time scale. It'll be temporarily stored, buffered, shredded, reworked, weathered in the floodplain, but as a whole, it doesn't have long-term preservation potential. That is only reserved for the areas marked as a sediment sink. So now we have a map of the sinks, but we need a new data set to distinguish between the uplands of the world, these sediment sources, and the lowlands that are bypass regions. And for that, we're going to go to a paper by John Pelletier and others back in 2015. In this paper, they were working to map the regolith and soil and sediment thickness around the world, which is cool, but not what we're going to be using as an input here. Instead, their method required applying one method to uplands of the world and a different one to the lowlands of the world, which means they mapped the uplands and lowlands of the world. I'm not going to go into full detail about how they do this. It involved a series of geologic mapping, roughness indices. They had to handle glacial areas differently. They had a global flow routing algorithm where they basically inundated the whole world with, I think, about half a centimeter of rain and allowed it to flow down and accumulate, and wherever it pooled past a certain depth, it can be lowland. But it does a pretty good job overall. I'll say that for our specific use case, there are some areas or types of areas we identified that we were able to refine a bit more. Here's an area in the northwest, I believe, of California. And what I want you to do is just take a second, look at the top left satellite, look at the top right elevation map, and think to yourself, which of these places are sediment sources, uplands, and which places are lowlands? How would you classify it? I see a whole bunch of mountains and just a few progradational deltas. This is how the input data set classified it, lowlands and uplands, and then this is how, after a series of refinements, we classified it. And just to illustrate the difference a little bit more, why I think it's a bit more fit for our purpose, I drew 3 cross sections here, same extent on all 3, and the color, the only difference is the bottom left is colored by the input data set, and the bottom right is colored by our interpretation. And we're a bit happier with ours just because it recognizes the mountains as sediment sources. It's a bit more useful for our purpose, but we're happy with it. We're happy enough that we just had a couple little last refinements. We just had we marked the lakes of the world as sediment sinks, intertidal areas, just to make sure the coasts were mapped nicely, and a little bit more. But now's a good time to show this global map, right? What's it going to look like? Is the world going to look like that diagram below? You tell me. We mapped the world at 250-meter resolution, so the pixel size was 250 meters, 16 per square kilometer. And to get back to the question, does the world look like the diagram? Some places it absolutely does, especially passive margins, especially places with big rivers. You get a really nice concentric ring, you know, like filling up a bathtub. You get the source, and then it goes into the bypass, and it goes into the sink. Places that have had a lot of time and sediment to prograde out into shallow basins look a lot like a source to sink diagram. But not everywhere in the world does. This is an area in Scandinavia where previous glaciation has scraped this landscape pretty flat. It's a hard cratonic rock. You have these tiny pothole lakes everywhere. You don't really have the opportunity to build up big drainage systems or to transport a lot of sediment. And in those types of areas where you don't have big rivers and you don't have a lot of sediment transport, it's harder to interpret it using that framework. The framework doesn't seem to apply as readily to those types of areas. And there's some stuff in between. I want to show you an example here from the Kandahar province of Afghanistan. I'm just going to set something up. Okay, so here we are. This is an area where we have a foreland basin in the foreground, and we have mountains in the background. Again, I just want you to think, how would you classify this as a source to sink system? Where do you think is going to erode, and where do you think sediment's going to accumulate? And here, this is a 3D render that I made in Blender. and I'm going to overlay. And overall, I think it kind of fits what my assumption would be, my heuristic kind of understanding, right? The mountains we see as sediment sources, erosional areas. The big sediment-filled basin in the front is correctly identified as a sink. And if I can zoom in a little bit on this right side, just to illustrate a little bit more, one thing I'm really happy, and I need to again give a shout out to the Nyberg and Howell data set, their work, is they managed to do a great job mapping the alluvial fans of the world, right? So if you look at that mountain ridge that kind of goes from the top center to the center right, the exposed bedrock on the top is absolutely erosional, but those fans that are coming off of it, those are storing sediment, right? They're building up fans, and it's correctly identified as a sink, even though it's steep. And so by leveraging these previous works, I'm quite happy with what we were able to do here. Happy enough that we can zoom out and look at some global questions. First things first, what's the overall global abundance of source to sink system domains? This is excluding Antarctica, but if you want to include the oceans, the world is mostly a sediment sink, the oceans. But if you're just looking at land, the world is mostly eroding. If you want just a textbook or lecture quote, I'll say that about 60% of the land is a sediment source, and then 20% sink, 20% bypass, give or take. But that's not true for all elevations. If we split the world up by how high it is above sea level, that top bin there is the elevation of, the distribution of source to sink domains across everything above 3 kilometers, the frozen ceiling of the world, the tips, and it's mostly erosional. And you get that as well down to 1 kilometer above sea level. You get a little bit more of a sink, but not too much until you get to the bottom. And if you're within 10 meters of sea level, or 3/4 of that area is in what we believe is a current actively subsiding or active sedimentary basin, which when we think back to interpreting the rock record, I think it's a bit of an idea that we know the stratigraphic record is a biased sampler, a biased narrator of Earth history, but I think this kind of helps us remember that it's telling the story of flat places and of low places more than anywhere else. So I always bring things back to rivers just because I love rivers. And sorry, just give me one sec. And I want to say that we can apply this and use this to study individual rivers and catchments. So here, I imagine some imaginary landscape. We have some river watershed where we classified each cell near each pixel as a sediment source, bypass, or sink. The easiest analysis is to look at the relative abundance across the catchment area, and we can see, okay, excellent. Here we have uh, more than half of it's a sediment source. Then we have some bypass and a sink. Excellent. But there's also a river that goes through here. And there's another way we can look at this. We can look at what the river experiences, and for every pixel, every cell that it crosses, we can sample and record what it experiences. And in this case, it experiences less source and more sink because it seeks low land. That's it applied to a synthetic data set. Let's apply it to a real one and a big one. This is the Amazon River watershed. Across that whole dashed black area, the relative abundance of these 3 domains is about 45% source, 45% bypass, 10% sink. Remember, there's a lot of bypass here because it's a full sedimentary basin, like we discussed earlier. But we can also look along the river. And as we go the 6,000 odd kilometers that the Amazon chases, we can see what looks kind of like a source to sink system, right? We can see we move from these erosional areas. We can recognize features like it shows up really nicely where we leave the mountain front and enter the foothills, the thrust belt, where you have these alternating bedrock and infilled sedimentary small basins into the foreland basin we see in the green there, and then the bypass, and eventually the marginal marine basin. So that's the analysis applied to one river. We applied the same thing to 12 of the largest rivers around the world. And if I could illustrate one, this is the Amazon, which we just looked at. Again, it's the same idea, catchment on top, river experience below. But we can also compare it and look at something like the Congo, where the catchment isn't too different, a little bit more source, but the river experience is a much different story. It keeps alternating between these sinks and bypass zones, and I mean, it does have to incise bedrock at some points when it hops from basin to basin or approaches the waterfront, but overall, it looks a lot different. I'm not going to talk about all of these, but just highlight a couple examples. The Yangtze is another one where almost the whole catchment is erosional, and the river doesn't leave confinement. It's in a sediment source for about 60% of the way. And if these sources are what are generating climate signals that are recorded in strata elsewhere, it might be different how far away the sink is. Now we can look at something like the Murray-Darling in Australia as a contrast. This is almost entirely in a intracratonic sedimentary basin, really high preservation potential. So overall, what I take away from this is generally, on average, these things do go from sources to sinks, right? It's not a bad assumption, but there's a ton of variability both between the rivers and along the rivers, how they go from domain to domain. And if I had another takeaway, it'd be that the mean abundance across these systems, the catchments tend to have a lot less of a sediment sink than the rivers. So the preservation potential of these 12 large rivers, we're guessing almost half of their length could be potentially preserved, which is a bit surprising for how big these rivers are. So that was analysis applied to specific rivers. Now, the question is, okay, we did this manually. Can we generalize this and think about something more global? And here we want to categorize rivers based on stream order. It's this idea that, okay, we can organize these things independent of width and discharge and drainage area. And we can just think as a network that the headwater channels, the absolute upstream tips of these river network systems are all rank one. And wherever two headwaters join, tributary, downstream of the tributary is rank two. Wherever two twos join, it's a three. It's just a way of ranking the rivers. And this is applied pen and paper to a single catchment, but in the geospatial data revolution, we have data products that represent the stream order across the world. And this is one applied, again, to the Amazon River Basin, where the brighter colors are higher order, goes up to, I believe, 10 at the main trunk channel. So if we take all of the first order channels around the world and we just look at the relative abundance of source to sink along their length and contrast it to the global land relative area, just a null hypothesis, let's say, you'll find that disproportionately they are erosional and not very depositional in terms of a source to sink system. So the preservation potential of rivers from order 3 and smaller is less than you would get from just the land average. And if it's order 4 or larger, it's more likely to be preserved. It's disproportionately made up of sediment sinks to the extent that 8, 9, 10, it almost becomes the majority. So that's the end of part one. Let's do some key takeaways. What did we learn? Well, our main question was, does the modern Earth surface actually look like a source to sink diagram? I'll say that some places absolutely do, particularly passive margins associated with large rivers, coincidentally where the source to sink model was developed in the first place. But even in areas that resemble the classic progression, there's a lot of variability along those rivers and between them, if you think of those 12, right? And on the other hand, some places don't, especially spots without substantial rivers. And so if much of the world isn't explainable by kind of the dominant framework we use to understand Earth surface processes, it suggests that we need some kind of revision or update in order to address the large parts of the world that are sedimentologically inactive, even if it just means adding a fourth category. And I think a process takeaway that I make from this is that rather than a decoration on the diagrams, right, the doodle I drew in the bottom, those blue lines, rather than just being a feature, I think that these rivers actually create the source to sink systems as typically drawn. They rearrange landscapes, move sediment to make them look more like the diagram. So they are not just inhabitants of their landscapes, they are authors of their landscapes. All right, that was the end of part one, where we tested the first community hypothesis, the source to sink framework. Now we're going to be moving on to landscape evolution modeling, just taking a note. We're moving into landscape evolution modeling. So if we compare these two doodles, right, the schematic I drew on the left, the one I drew on the right, the first part of the talk was talking about the fate of sediment, the fate of the landscape. Is it going to erode? Is it going to deposit? We don't really care how or when it happens, but just long term over these 10 to the 5, 10 to the 6 year timescales, is it going to be preserved or not? Part two on the right is going to be talking about how it moves. So instead of talking about the destination, it talks about the journey. It talks about the process. Which physical processes are responsible for describing how the Earth's surface evolves in each location? So I want to just go back a little bit. Please indulge me. I'm a sucker for a little bit of history, and I want to talk just about what I think of the origins of Earth system modeling. Late 1800s, around 1900 or so, Cleveland Abbey was working on weather forecasting and had what I think is a great idea. Essentially, previously, if you wanted to forecast the weather, the idea was to use statistics and repetition of patterns. So if it is windy in the third week of April in this part of England, this year, let's look at the last time it was windy in the third week of April in this part of England, and whatever happened the rest of the year last time is a good guess of what's going to happen this year. That was how it worked, but he kind of saw this. No, what if we represent this as a series of equations? If we represent mass transfer, heat transfer, momentum transfer, conservation, we should be able to eventually uh, represent this more physically. And so in 1901, he set up something that here, if the landscape evolution modelers in the room should find this very familiar, a system of 7 equations and 7 unknowns, which is solvable now, but he fully knew that at the time there was no way to numerically solve this. There's no way to analytically solve it. Even graphically, there weren't very good solutions. So I think the point is, though, if we can understand the physics of a system, the underlying mathematics well enough, the computations will follow. And they did. By the 1960s, we had global atmosphere circulation models working off of similar premises. We had global ocean models in the 70s. We had global mantle models in the 80s. So when did we get global landscape evolution models? Right? If back then we figured out the air, we figured out the water, we figured out underground, when did we figure out the surface of the ground? Doesn't seem like it should be that much harder, right? Geomorphology, we didn't get our own governing equations until at least the 1960s. And even then, okay, so once we had them, we pretty quickly implement them in local domains, but when did we formalize and put them into global models? It was relatively recent, right? 2010s, 2020s. Tristan Sal's group has put out a series of really cool papers with these global landscape evolution models through deep time, where the spatial, each pixel is 10 kilometers, the time step is a million years, which is a bit long, but it's still a very useful for some questions, and it's advanced our discipline. But the point still remains that why do we seem to be coming to the table later than our sibling disciplines? I'm going to argue it's because those other systems, atmosphere, the ocean, the mantle, can all be represented analytically. It's a convection problem. And we have pretty good physics. We know Navier-Stokes equations, simplifications of it. We have this idea that if you have a single equation or set of equations, you can apply that to every single spot on the world equally, and it'll tell you how mass moves around and at what rate. And there will be assumptions involved, but we have a universal governing equation. In geomorphology, we do not have this. We have heuristic estimations, which Bill Dietrich called geomorphic transport laws. Greg Tucker and Hancock later said transport functions. Um, Mike Church as well, I know, had the own thoughts on the matter, but the idea is still fundamentally that we don't have a single equation that applies to every spot in the world. Instead, we have these heuristics that rules essentially that we have a set of rules for rivers if they're bedrock, and then a different set if they're alluvial. You can't necessarily use the same equation to explain both. And we have something for hill slopes. You can explain how mass moves around. If it's soil mantled, it's diffusive. If you're bedrock limited, then we need an advective component. Windblown, aeolian, glacial, lacustrine, depositional environments, all these have different quirks. So how do we make these large landscape evolution models? Historically, the main path has been to simplify and just say, look, we can get most of the mass moved around correctly if we just have two. We have a soil creep, which is diffusive, and we have bedrock river incision, which is effective. And it's a reasonable assumption, probably. It certainly works and it's been calibrated, and on catchment scale, it works. But my second question here is, how well can we represent the Earth's surface evolution using just these two processes? So as an illustration of this point, I'm going to bring up this doodle again with all these different domains, all these different parts of the landscape, and make the argument, the pitch that hey, if we're only representing two processes, but they make up a small fraction of the land area, maybe we're overplaying our hand. But I think a reasonable person could come to me and say, "Oh no, Harrison, that's a weak argument. You drew both those doodles. You chose the proportion of those different domains. You know, how do you know that hill slopes don't make up more of the world?" And to that, I would answer, you're completely correct. We do not know the relative abundance of different geomorphic process domains around the world, so we need a global map, and that's what Mike and I did. So the first step, again, and I'll go quickly, is to find and harmonize data sets. So you look to the subject matter experts, you look to the river community, you find all the maps of rivers, you make them work together nicely. You run them through another decision tree. I'm definitely not going through this one. It's just suffice to say it's a lot longer, and there's a lot of input data sets. And these are based on remote sensing, modeling, a lot of machine learning, geologic mapping, field mapping. But at the end of the day, these are all each discipline's kind of best guess or most advanced understanding of how their area of interest is distributed around the world. So we put them all together, and now I'm going to show you the global map with these domains. Here it is. So the domains that we mapped, glacial, so the glaciers, the perennial ice parts of the world, places where lacustrine, so the lakes of the world. We have alluvial rivers and bedrock rivers, which are really just governed by whether you think it's non-cohesive material on the bottom or if it's incising into bedrock. Aeolian, bedrock limited slopes, soil mantle slopes, and eventually flatlands, the last one. If you're wondering what's a flatland, we classified it as saying, hey, no other domain applies here, and it's flatter than half a degree. So if we can't identify anything else going on and it seems flat, we're not sure what's going on there, but it's going to be a class of its own. And again, to zoom into the Kandahar province as an illustration, we're also then going to go to Trenton, New Jersey, and I'll show what it looks like there too. So if I optimize for video sharing again, once again, I encourage you to pick a spot in the landscape, focus on it, and think how you're going to think about how you expect it's going to be represented in the map. I'm happy with how it pulls out the Aeolian dune fields, right? That gold area. It maps out the river channel belts pretty nicely. I'm really happy with how it captures the mountain tops, right? The exposed bedrock versus the soil mantled slope beneath. And I'm going to zoom in again on that area to the right, where here it does, I think, a pretty nice job, especially talking about the Aeolian versus flatlands and that transition from bedrock limited to soil mantled on the slopes. And it's pretty decent in terms of the false positive and false negative rate looking at rivers, right? It doesn't imagine too many. It doesn't miss too many. Here in the Trenton area, I just wanted to show this because it's more tectonically active. It's a pretty interesting area. You can see how it captures the tops of the mountains as being bedrock limited, soil mantled elsewhere. But really the thing I wanted to show here is how it's able to capture these small rivers that drain the valleys, and if they're bedrock or alluvial, the more flat ones. So that's enough, I think, for us to zoom out again and look at this global map. And here it is a histogram where each column and each row is its own, a map where each degree of longitude, each degree of latitude is its own histogram, showing the relative abundance around the world. And we just, first of all, look for broad trends, right? The top and bottom of the world, highest and lowest latitudes are dominated, or at least most common, glacial. The Aeolian transport regions show up around the extratropical aridity bands, not so much in the tropics. And most of the world's lakes, this is something I learned, most of the world's lakes are boreal. They're above 35 degrees north. They're in the northern part of the world. So I'm not going to go through all these, but if we're thinking that eventually we're going to want to bring if we think that eventually we're going to want to bring these other domains into these landscape evolution models, we have to think about how do we predict where they're going to be. So it's worth looking at correlates, right? So here is the distribution of these different process domains against moisture. So if you look at the bottom, it's an aridity index where the topper bands are wetter, more humid, and the bottom are drier. And we can see that the more humid parts of the world, you have more glaciers, you have more of the area is taken up by rivers, and at the bottom, the driest parts of the world, more of the area is taken up by Aeolian dune fields. This is what we would expect, but it's cool to see it. Same story with temperature, where the hottest parts of the world tend to be where we have the most Aeolian dune transport, and the coldest parts are where we have the most glaciers. Again, it's intuitive, but interesting to be able to test and figure out what those quantitative limits are. So going back to that governing question, right? Can we fairly represent the Earth via these two processes, soil creep and bedrock river incision? Well, let's go from left to right here and let's look. About 2% of the world is air by area outside of, again, excluding Antarctica. 2% of the Earth area is glacial. Another 2.5 is lacustrine, so lakes. 3% or so is alluvial rivers. Half is bedrock rivers. 4 and a bit is aeolian. These are really, really important processes sedimentologically. They move a lot of material around the world, but they don't make up a lot of area. And I think what's more telling is if we're just using soil creep and bedrock river incision, it's encouraging that about a third of the world seems to be a soil mantled hill slope. And really, though, to answer this question, we need to figure out what flatlands are, right? Because if flatlands can be represented by soil creep easily, then we're doing great. We got 3/4 of the world already, and we can just refine the last bits. So what are flatlands? I will confess here that I have been playing a semantic sleight of hand, a little bit of trick on you all, in that I've been calling flatlands, I've been counting them with other geomorphic process domains, but they're really not. That is a geographic distinction. It is a physical description of a landscape, not a process description of how it changes over time. So when Mike and I were working on this, we saw all these flatlands. We started thinking, what is going on in these parts of the world? How are they evolving? Because we don't often think about how the flattest parts of the world evolve and geomorphically change over time. So to answer this, I randomly picked 50 flatland points around the world and I did detailed investigation of each. I went through satellites, elevation maps, a lit review for any studies I could find. I went through geologic maps and surface geology maps just to put things together and figure out what's going on in each of them. And fortunately, almost all of them fell into one of three classes. The first one here I'm going to show in the foreground at the bottom of the page picture, you're going to see a river corridor. It's an alluvial channel belt. Totally cool. But that top part, that upland, the really flat spot, what is that? That is a tableland. The idea here is tablelands, sorry, optimized for video again. Tablelands are where you have laterally extensive and resistant sedimentary deposits. It could be clastic, it could be carbonate, but either way, it is hard for the earth to erode down there. And so generally, it doesn't erode top down, it erodes sides in as gullies evolve or as you get rockfall. So that is the first category, these tablelands. But the next one, here's an example from near Kagulu Hill in Uganda. What is this one? It's a shield. It's a basement. It's a cratonic or a plutonic spot, crystalline, metamorphic, igneous rock. I'm using a lot of terms, but what this really means is very, very hard rock that's been eroded very, very flat. And I think there's some really interesting process questions about how that happens, but that'll be for another time. But still, about 40% of the flatlands that we tested or spot checked were tablelands, another 20 were shields, and almost all the remainder were a category that's very near and dear to my heart, depositional. So this is where these rivers, generally rivers, but essentially depositional, where sediment has been carried out, and if you're prograding, so if you're building land out into shallow seas, it is way easier to fill something up to sea level than to build sediment above sea level. So they tend to make very flat landscapes. So we know what's going on along these rivers, but it's a little uncertain what's going on in between them. So, okay, we identified three main classes of flatlands. What does that tell us about process? The first thing I'll say is the first two are actually erosional. They are sediment sources. They are those flat erosional areas that we had so much trouble identifying in the first part of the talk, where the model doesn't seem to work so great. Based on a limited, and I highlight limited body of literature that I was able to find, I did some looking, and I'm happy to hear from this community. I would love to hear more, but it seems like the few times these have been represented in process models, people use topographic diffusion, mostly because it lets you build something flat. So that might be reasonable. Now, the depositional 40%, how are these landscapes usually modeled? I'll bring you back here to this idea that we know what's going on along these rivers, but we aren't quite as sure. It's not immediately clear what's happening between the rivers. And in order to illustrate that, I have to explain avulsions. So you can see the river at the top, you can see the river at the bottom, there's two of them. When and where does the material in between, the land in between, get reworked? In what scenario is that going to get moved away and mobilized? Well, in this case, it happens when the river avulses, when it suddenly changes position to a new spot, a new course on its former floodplain, and all of a sudden, what used to be this flatland is now there's a river channel belt there. It changes definitions, and so understanding depositional systems in the context of landscape evolution modeling means we're going to have to understand avulsion timescales and these weirdly fast events that happen very infrequently, which is tough to model. If we're used to making the assumptions of equilibrium continuous, that you can represent something long by a whole bunch of little things, or you can represent the sum of a whole bunch of little things as something very long and continuous, it's going to be challenging to put into a model. But we do model them. They are modelable. There's nothing about avulsions that means we can't model them. It's just that we have to deal with a different time scale. This is a model I put out in my PhD with Doug Edmonds, where we're able to recreate these mountain front landscapes pretty well. But the problem is we need to be able to, excuse me, we need to be able to represent them at an appropriate time step. We have a 10-year time step here, and that's not usually what we're representing these large landscape evolution models. There have been some attempts to develop generalizable predictive models. Vamsi-Ganti had a paper about 14 years ago on using some fractal and long-tailed statistics math in order to get generalizable. But I think this is really a route forward. If you're developing a large landscape evolution model that really needs to represent depositional areas correctly, for example, if you're building the rock record, I think that this is a good route forwards and something that we as a community should work on. So, quick logistics now that I have more or less finished part two. If you're a data nerd, this is going to be music to your ears. If you're not a data nerd, you can zone out for the next 60 seconds or so, but I love this stuff. When we made these maps, I made them so that the two are interoperable, which means they have the exact same resolution, exact same spatial extent, exact same projection. So you can pull them into MATLAB or Python, and it's just overlaying one one matrix on another, and the math, it tends to be pretty easy. They're optimized for storage and read-write speed. So for the source to sync one, for example, it's distilled from more than 5 gigs of data, but I got it down to 38 megs. I saved everything as an unsigned 8-bit integer, so it's nice and crispy. Free and open source repository. So for the source to sync map, the geomorphic one isn't there yet. The paper's still in review, but once that's finished, I'll be uploading as well, where it has the outputs, it has the code, it has instructions, and all the intermediate data products. So if you want to recreate this map locally, you can just download the code, change the directory, hit run, and you're good. And the other thing is I really optimize the computational time, the scientific computing. So we can recreate the global source to sync map in 10, 15 minutes. And this was important for development because we could change something in the decision tree. We could swap out a data layer or make a different order of events and regenerate Western North America in about 15 seconds. And last but not least, if you're not a data nerd, you still might like this. If you're just interested in looking at this data set, if you just want to zoom around this map, you think it'd be fun, you don't need any special software, you don't need any special skills. Go to source to sync.mapsof.rocks. Worked on this with my good friend Eric Michel, and we put together this web map where you can go through without any specialty software and just check it out. The QR code is here and it'll be on the last slide too. All right, let's finish up with some key takeaways. We tested 2 community hypotheses today. The first one, source to sync framework, does the modern Earth actually look like the diagrams? Well, to answer it, we mapped global source to sync systems for the whole world, and some places absolutely do, especially active margins, passive margins with big rivers, although there's a lot of variability along the way. And there's a lot of the world that doesn't really easily fit this framework. And I think for the framework to address the whole world, we need to adapt it in order to be handle the very common but very understudied sedimentologically inactive parts of the world, especially the flat parts. And that relates a lot to part 2, doesn't it? Where we asked if soil creep and bedrock river incision are sufficient to represent the Earth in these big LEMs, landscape evolution models. To do this, we mapped global geomorphic process domains, and by area, 3/4 of the world is a soil-mantled hill slope or flatlands, which maybe we can represent flatlands by diffusive soil creep, but Man, flatlands are critically understudied relative to their abundance, especially considering how many people live on them. And finally, depositional environments in particular, I think they need better geomorphic transport functions that cross this timescale gap between the decadal scale erosion models and the millennial plus timescale landscape evolution models. And all this, last but not least, unless we discover a universal transport function. That'd be great, right? If we just had one equation where correctly parameterized, we could apply it to every cell around the world evenly. That would be wonderful. We could push the field forward. But unless and until we discover that, I think that the roadmap we've laid out here is a good way forward. I want to thank sincerely my co-author, Mike Lamb, my supervisor and mentor here at Caltech, for co-authoring the first paper with me and the second one that's currently in review. Caltech's Division GPS funded the first year of my postdoc here, and the Resnick Sustainability Institute is currently funding me. And I want to again thank the organizers for a wonderful series. Feel free to ask questions now, or you can go to my email address or check out the website as well, harrison.studies.rocks. If you're watching the YouTube recording, the contact form's always open there. Thank you so much.
Thanks a lot, Harrison. That was great. You're getting a lot of clapping. Hope you can virtually hear
Mhm.
that.
Oh, so many
Uh,
claps.
How many claps?
yeah, a lot. Yeah, very nice. Thanks a lot. I think, yeah, the chat is open for question. So please take the chance to ask. And also Tamara posted there, like
Mhm.
the link of your source to
Your
sync.
map.
So that,
Yeah, please. I put the link and I start looking at the website. It's really cool to play around. Thanks so much, Harrison. That was a great presentation. Well, we wait for people to ask and pose their questions right there in the chat. I have some questions I would like to ask you to start. So, well, I have a few questions, and I like a lot of the statements you made, and definitely I might use them for teaching the classes. But um, one of the things I had a question about, you mentioned in the first part of the talk that there was some type of correlation between passive margins having more of the sink and having this more traditional framework. I don't know if you went farther to check on this, but I'm sure you might have some insights. But on the non-passive margins in the active tectonic regimes, do you notice any patterns between type of tectonic context, like if it was what type of faults? Because I'm thinking like if you have tectonic context that is generating a basin versus something that is uplifting a mountain, like do you have any insights on that? Is there any correlation between tectonic regime? Oh, I
Yeah,
think I see it now.
absolutely. So I just threw up a bonus slide. So I didn't present this today, but the 12 big rivers around the world that we studied, we also looked at the climatic trends along them, which I'll sorry very quickly throw up. So we measured the aridity and the temperature class along each of them. Not a lot of trends, to be honest. I was surprised.
Mhm.
But tectonically, there is some interesting stuff. And forgive me for a bit of a messy figure, but one of the things I found really interesting is in the proximal part of the system. So the upstream most, right, kind of in still in the mountains. There's a big difference in the types of basins of sinks that you get than in the medial or distal. So most commonly, you'll see here, most of the mountainous upstream basins are actually extensional, or a lot of them are extensional lakes. Some though, like the uh, some of them are anthropogenic, so the ones that have an H there. About half
Mm.
of the upstream basins, the mountainous basins that we looked at, uh, are anthropogenic dams, dammed lakes. And so I do think there's a fun thing about there. Are we creating an unprecedented upstream sedimentary record? I don't know. But downstream though, there's a lot of passive margins you can see, the Nile, the Mississippi, the Amazon, and foreland basins as well.
Okay, great. Yeah, this wasn't prepared. Oh, this question wasn't prepared. It's good. You had it.
I
Yeah.
promise we didn't coordinate this ahead of time.
Oh, thank you so much. And we have some questions in the chat. I'm gonna read the first one, Elena. So we have Orencio Duran who is asking, what do you mean by a universal sediment transport equation? And what do you think is the role of vegetation on landscape evolution?
Perfect. Okay, so universal transport equation. What I mean here is that if we look at how people will evolve the atmosphere, let's say, we they essentially have a series of equations that you can apply to every single cell in the world. And if we think that we got the equations right, and if we think we got the parameters right, and we didn't make any math errors, we can describe how mass moves everywhere using one equation. I think that heuristically, if we want to describe, for example, how sediment moves down an alluvial river, you could use Payola 92, a diffusion equation to describe how sediment moves along a river, but that's not going to be a valid equation that also applies to aeolian landscapes. Or similarly, there are a couple mass transport functions for how sediments eroded under glaciers, right? Some function of, I think it's glacier thickness, non-dimensional scalar, or no, glacier thickness, a parameter, and basal glacier velocity, I think it is. Essentially, we have an equation that we can use, and we do use to describe erosion under a glacier, but it's not going to describe erosion underneath a bedrock river. So when I say universal transport equation, it would be the assumption that uh, we could discover some equation where if you could combine all of them in a meaningful way, and right now we're not there, but that's really what I was implying. And the role of vegetation, completely agreed. It is huge. And my own background, I come from the meandering river world. That's where I spent my PhD years cutting my teeth, and the role of vegetation there is huge. There's the whole question of, did we even have meandering rivers before vegetation? And there's good reason to believe now that we do, but it's a big direction for the field. I think that I at one point did try to correlate all these different domains to a pretty coarse vegetation map. It was like shrublands versus dense forest versus light forest versus grasslands. It worked okay. It wasn't convincing enough for me to publish on, but I think that there's room for more study there.
Cool. We got another question from Bruce Wilkinson. It says, super talk. Maybe a matter of time scale, New York State. At a scale of the Phanerozoic, mostly sink. At a scale of the Holocene, mostly bypass. Most of the Mississippi Delta system is now relatively bypass.
I couldn't agree more. The distinction, oh, sorry, that was the wrong slide, but the distinction between source and sink and bypass is very timescale dependent. Let me finish pulling up the map, make sure I'm looking at the correct one. We'll use this one. Right, so I completely agree. The Amazon example, for you could look at any of the large rivers that move along the Amazon. You could say that they are temporarily on the scale of years to decades to maybe centuries. Actually, no, channel belts. Emily Guyman, a colleague here, has done some great work talking about the turnover time and age of rivers in meandering channel belts, and they can go up to 10,000 years at a point. So we really need to set a timescale limit on what we consider a source, a sink, and a bypass to make sure we're talking about the same thing. And I'm really thinking on a geologic or stratigraphic timescale here. So in the paper, we really emphasize it's kind of on that 10 to the 5, 10 to the 6 year timescale. You could also argue that, right, so something is a sediment sink, it's going to be preserved until the tectonic regime changes, and now we're uplifting, and oh no, we're eroding it. Was it ever really a sink? So we have to set a time scale. The other example I give is the Western Cordillera, where it was collisional until about 50 million years ago and then started extending. And so we're converting areas that used to be sources now are these really proximal sinks. But I agree.
Great. We have another question in the chat from Piotr Migon. Sorry if I'm mispronouncing your name. So the question is, were the table were the tablelands 38% of flatlands identified by simple overlay of geologic map showing sedimentary rocks on the slope map, gradient less than 0.5%? What about large scale tilting?
It's a great question, and it's one of the scary things about doing these kind of big global scale projects, right? It's easy for us to wave our arms and kind of swoop in and say, "Oh, we've explored the world," you know. But uh, there's always the potential and really the opportunity to be corrected by folks who do local work and who've spent a lot of time studying specific field sites. I really want to acknowledge that, and uh, I expect and encourage folks to look at the maps and berate me a bit if I got their favorite area wrong, which is good for the field. But to answer your question more specifically, the first step, yeah, was overlaying a geologic map, looking for stuff about the right lithology, about the right age. A lot of it then came into looking at satellite imagery, trying to find any kind of outcrops, trying to identify that we had distinct edges that were advecting inwards, which helps. If you have exposed bedrock, you can look at the dips too. I would also try and go through papers that have been published on that area where people have reported measured dips or interpretations. At the end of the day, it's a bit tricky because we don't know for a fact how thick the soil cover is there, right? You could imagine an area that's a tableland, but hasn't really been uplifting for a bit. It's there's not a lot of rain going through. There's not a lot of it's really far from the edge. And so you can imagine there you have thick soil profiles developed and geomorphically maybe it no longer behaves like a cap rock, you know. It's tough, but at a certain point we kind of had to become lumpers instead of splitters to try and make a point and create opportunities for future refinement.
Cool. Thanks a lot. We just approached the hour, so I think we can close it here. And yeah, I guess we all thank you again a lot, Harrison, for this great talk. As I said at the beginning, it's recorded, so we will upload it on YouTube. And yeah, next week it goes on. And yeah, so please check our webpage for the next talks. And we look
Yeah,
forward to
and
seeing
as Harrison gave
you.
us this great information for the next week, we're gonna have Austin Chadwick probably talking about flatlands. So if
Okay, so
you want to see more
good,
about it,
good, good. So we continue on this. Yeah, but thanks
Austin
a lot.
does great work and gives great talks, so you should definitely check it out if you're interested in the rivers at all. I'll be there.
Cool.
thanks so much, Harrison. Thanks everyone.
Thank you. Have a great day.